Greetings and welcome to a new video about Miller's theorem. We will apply this theorem on a voltage amplifier having a feedback resistor, and we will see how that is affecting our voltage gain, input impedance and also the output impedance. So let's see that clearly in this video. Of course we will see everything step by step in our calculations and verify this in SPI simulations. Okay, we have a non-ideal amplifier having a feedback resistance, and this circuit is shown here. We have here the following parameters: the source resistance, the load and the feedback resistance here, and we have also the model of our voltage amplifier. Our objective is to determine the closed loop voltage gain given by T of VO over VS of this circuit using Miller's theorem. Now first we will discuss the voltage amplifier model. In here you see the voltage amplifier model, and that is given here in this pink box. And you see here the RI, RO and the voltage controlled voltage source having a value A0 times the VI. The parameters are shown here: the input resistance, output resistance and the open circuit voltage gain. What is an open circuit voltage gain? Well, the gain here for the condition where you have the output nodes of your model of your voltage amplifier opened. In the ideal situation, the ideal amplifier will have an infinite input impedance or input resistance. The output resistance will be 0, so it will be effectively a short, and this will be effectively an open, since this is an infinite. And the A0 value, which is open circuit voltage gain, is also infinite. That's most of the time what you consider in the first try, and then make the model more accurate and close to reality. Now when we use our Miller's theorem, we will convert this circuit into this circuit where you see the RF is disappeared and has now created two resistances are in Miller in the input nodes between this node and that node, which is also connecting actually your model, and also between this node and that node where you have an R out Miller. So we can now transform the problem which has a floating resistance or floating element into two elements connecting between the input here and also between the output nodes. And that will be of course easy for our calculations, so we'll continue. First we designate the node X and Y here and also the same nodes there. We start first by considering and defining our open feedback voltage gain. What does it mean by open feedback voltage gain? Well, we break this loop in the feedback open, so this will be an open network. And that will be then the voltage gain, I call this AXY, from this node to that node. So we go from this node to that node only by not considering the RF. And that is effectively actually going from this node to that node and from that node to that node. So don't make the mistake going all the way from the input all the way to the output, but it's only from this node to the node Y. Why? Because that is also where the feedback element is connected. Now that's then divided here in two parts, because the gain here or the value here is A0 VI. That's the value here divided by the VI, because that's the first try. And then you do the output voltage here, which is also the VY, divided by this voltage, which is actually A0 times the VI. So we have now effectively A0 times the voltage divider here part in this region. So we can divide the problem in two parts, in the red box here given and the blue box given. So our formula for our open feedback voltage gain will be then A0 times RL over RO plus RL. Now we can continue, because this is what we need in order to go to the Miller input resistance. And that's then given by this formula. We have discussed this in the previous video where we considered the Miller's theorem and also derived the formula for that. So we have to divide our feedback resistance here by 1 minus this open feedback voltage gain. Now we have the value, and we can also do that for the R out Miller by doing a similar expression we have discussed also in great detail in the other video: RF over 1 minus 1 over this open feedback voltage gain. Okay, let's now use some numbers to get a better understanding of the situation. So we have the following values for our model of the voltage amplifier: RI, RO and A0. And this is the source resistance, load and the feedback resistance given. So if you substitute now these values, you get for our open feedback voltage gain here the value of minus 90.91. And using that we can now calculate the R in Miller, and that will result in 10.88 kilo ohms. And our out Miller here will be then, again, using this open feedback voltage gain, will be 989.12 kilo ohm. You see actually this RN Miller has reduced significantly from actually this 1 mega to almost, let's say, 10.9 kilo ohms. But the Miller output resistance is close to what we actually had before RF. This is most of the time also the case if the gain is large. Okay, let's go to the closed loop voltage gain. Well, for that we use this equivalent circuit. It's more easily done in this circuit instead of this circuit. So what we do actually, we have now here two parts again. We have the VO over VS that we need to calculate, but we can divide the problem by looking at the situation that we have two resistances here in parallel. I call this, for example, Rx. And I have also the two resistors here parallel, which is R out Miller and the RL, and that's also what I call as RY. So I can take the two resistances, taking that together and make again here voltage divider rule and then go out all the way to the output. So I can say Rx over Rs plus Rx times again a 0, because from this node to that node that the gain is a 0. And from that node to that node I will apply again the voltage divider rule, Ry over Ro plus Ry. What is Rx? Well, you use the formula for the two parallel resistances, and it will result here in 10,868 ohms, and for Ry it is 998.99 ohms. Well, you substitute that values here in the closed voltage gain, you get here minus 47.34 as the gain. And now we will of course verify this shortly. We have now here the situation, and let's go to the simulation results for the values we have selected. And this is now the simulation circuit. You see here the voltage controlled voltage gain with the gain of minus 100, also the other parameters. I apply here Vs of 1 millivolts with a 0 phase, but the V out here is 47.344 millivolts with a phase of 180 degrees. That means it's already inverted, so that is a minus sign in our result. And it has a gain of this value divided by that. And in our calculations we had determined that the voltage gain was minus 47.34. And here from the simulations we do again this value divided by the input, and you will have minus 47.344. Now, well, this is almost the same, so we can say this is nice. Okay, let's see some situations here. So what will now be the voltage gain, the closed voltage gain, if we now adjust some values in the components? So is the Miller's theorem still valid? That's actually the objective of this situation. So we have here a couple of cases, in total 5. You see here again the parameters like the A0, Ri, Ro, they are exact same. Rs, but I will change here in the first try, I will change the feedback resistance value from 1 mega, I will change it to 100 kilo and then 10 kilo. And these were the parameters we have discussed for this circuit. So looking at the 3 cases and looking at the simulation results, the case 1 is already what we have discussed. Now case 2 is what you see here is the output voltage here for the situation RF is 100 kilo ohm is 8.919 millivolts. Now divided by this 1 milli, if you do the calculation there looking at the second column, it is close to what we see here. Now going to the case 3, where you see here the output voltage is 979 etc. microvolts. So if you convert that to millivolts, you will get 0.978 etc. divided by this 1 milli. So you get actually here an attenuation, which is this minus 0.969 what we have in the calculation. It is close to what you see here. Again, this 180 degrees because of this inversion. So that's all fine. Now going to the case 4 and 5, where there we have the Ri, which is now not 10 but 1 mega. And the other case, case 5, is where you see actually only changes now the Rs from 10 kilo ohm to 1 kilo ohm. So let's see the simulation results. Case 4 is here. So still 1 mega ohm here for the feedback, but the only change is now that the Ri is 1 mega instead of 10 mega. Now you see here the value, 47.12 millivolts. And we have from our calculations minus 47.12. So very close to what we actually see in the simulator. In the case 5, we say here 83.24 for the situation where the Rs is not 10 but 1 kilo ohm, and the rest are the exact same. And if you calculate the gain here, it is also very close to, in this case, exactly as we have it. So this is also perfectly fine. All right, it was our example. Considering the non-ideal voltage amplifier having a feedback resistance, we have used the Miller's theorem to determine the voltage gain in a more convenient way. If you have any questions about this example, please let me know and I will try to answer them as soon as possible. Another example, next one, we will discuss the voltage amplifier, but this time we have feedback capacitance and see also the effect on that on our frequency response. Stay tuned and see you next time in another video. Take care.